Okay, so this is the Honors Math 3, Unit 10, Objective 5 notes, and it's about domain restrictions. So we will be revisiting our graphing. We won't actually be creating the graphs, we will just be finding certain values that create sections of the graph. So that is what we're going to be working with. We'll also be working with solving equations. So if you think you are a little weak or rusty on solving equations, go back and look at previous objectives. So objective 4, objective 2, that sort of thing. Okay? All right, so let's go ahead and start with what we're going to be doing. So we're going to be looking for values of theta that will graph only pieces of our polar graphs. So maybe a single petal of a petal graph, or the inner loop of a limacone, or the outer loop of a limacone as well. So those will be the two main graphs that we will be working with. So in particular, we are trying to figure out the value of theta that passes through the pole. And that will always occur when the radius is equal to 0. So oftentimes we think about kind of our XY coordinate axis in which we have an ordered pair for an origin 0, 0, right? So that would be on your XY. But when we're working in polar coordinates, the only thing that we can say for sure about this dot here at the pole is that r has to be 0. Theta can be anything, right, depending upon the graph. So the only thing we know for certain is that r has to be equal to 0 when it passes through the pole. And so that is mostly what we're going to be doing, is solving equations for where the radius is equal to 0, and then understanding ideas of symmetry and reference angles to help us find that other value or values. Okay? All right, so let's go ahead and take a look at question number 1. So for this, they want us to find the domain restrictions. So we're going to call those alpha and beta, and we want to make sure that we are in radians. And we will be looking for those values that create the partial graph that is stated or given in each particular problem. So for question number 1, part A, they're asking us to find the inner loop only. So we're trying to figure out what does alpha need to be and what does beta need to be in order to graph the inner loop. So if I look at the inner loop, it actually will pass through the pole twice, right? One time when it's entering the loop, it has to start at the pole. And then when it's finishing the loop, it's going to end at the pole as well. And then just a reminder that the only thing that we know for sure about that is the radius has to be 0 in order for it to enter the pole. So that will be our first step, okay? So we're going to go ahead and take this equation right here that was given for our limacone. And we are going to let the radius equal 0, because that will give us our values for alpha and beta. So I have that equation 3 plus 6 cosine theta, and then replace the radius with 0. And then this would be a good time to press pause and go ahead and try to solve that equation, right? So we've done lots of solving in the past. So if you hit pause, solve it forward, and see if you got the same values as I did. So I'm going to go ahead and subtract 3 from both sides. And then divide both sides by 6, because I'm trying to isolate the trig function. And then negative 3 over 6 reduces down to negative 1/2. And so then now where I'm looking is where is cosine equal to a negative value. So cosine is equal to a negative value over in quadrant 2 and in quadrant 3. And then I know that theta prime would be equal to pi over 3. So let's get that common denominator over here at pi. So that would be at 3 pi over 3. And so then my two rotated angles from 0 are going to be right before I get to 3 pi over 3 with that reference angle. So that would be 2 pi over 3. And then right after that, and that would be 4 pi over 3. So those would be my two values when, or two of many, right? Because you can use all kinds of coterminal angles where you just keep circling around. So then what I have is, let me go ahead and erase this just to give me a little bit of room here. So what I know then is that alpha, oops, erase, sorry. Okay, so what I know is our alpha value here is going to be 2 pi over 3, because that's in my quadrant 2. And then my beta value that I just found is 4 pi over 3. So at alpha of 2 pi over 3, that's the start of my inner loop, and then it's going to rotate through and enter the radius equaling 0 at 4 pi over 3. So that's going to create my inner loop. So my inner loop value is created between 2 pi over 3 and 4 pi over 3. So you might be wondering, well, if it's between alpha and beta, which looks like it's over here in quadrants 2 and 3, why is the actual inner loop over in quadrants 1 and 4? And that would just mean that I know between alpha and beta over here, this is where cosine is negative, and I'm working on a cosine graph. And so if this is where cosine is negative, then that means my r is going to be negative between 2 pi over 3 and 4 pi over 3. So that means if r is negative, my graph won't occur over in the left quadrants, but will actually end up graphing over in the right quadrant, which is where that graph is, okay? All right, so let's go ahead and take a look at the next part of it. So the next part of it, so I'm going to undo a little bit here, is we want to graph or figure out the values for alpha and beta in order to graph the outer loop, right? So that is the second component. When will we graph that outer loop? So what we want to take a look at is we need to think about, okay, so what is happening with that graph? How am I going to figure out that outer loop? So what we're going to be keeping track of is I know that I start at 2 pi over 3, and then that's going to create that inner loop here. And then I stop at 4 pi over 3. So then what happens after 4 pi over 3? So after 4 pi over 3, I start to enter into the outer loop. So then what does that mean? So that means the outer loop is going to start where I left off. So I left off at 4 pi over 3, right? So if I look right here, so this is where I stopped graphing the inner loop, 4 pi over 3. So then that means that's when I'm going to start graphing the inner loop, right? So then, or the outer loop. So the outer loop will begin to graph at the end of the inner loop, so that's at 4 pi over 3. And so then now I need to figure out, okay, well, when will it stop graphing? So it's still graphing, right? So it's still graphing the outer loop, and then it's going to get to here, which is at 2 pi, and then it's got to keep going, right? Because I haven't graphed the whole outer loop, I've only graphed that bottom half. So I'm going to keep going, right? So I'm going past 2 pi, right? I need to figure out what do I add to 2 pi? How far past 2 pi am I going to go? And so I'm going to keep going until I get back to the inner loop section. Well, how far was that? Well, that was 2 pi over 3, right? So I know that to go from here to the pole again, because of symmetry, it has to be 2 pi over 3. And so that is what I'm going to add to the 2 pi value. So then my ending of my outer loop is I went past 2 pi, and I went past it by 2 pi over 3. And so then I just need to add those two values together. So then I would have 4 pi over 3, of course, is where I'm beginning the outer loop. And then when I add 2 pi to 2 pi over 3, and I get that common denominator, I'm going to multiply by 3, so that would give me 6 pi over 3. And so that plus 2 pi over 3 would be 8 pi over 3. And that would be my outer loop, is right there. Okay? All right, so just recap that one more time. So what is the kind of things that we need to do? So we need to let always that radius equals 0, because we want to know when it's going to get into that pole. And then when I solve that equation, which I should be pretty skillful at this point, I should get those two values, right? I should always get two values minimum, right? Because it could potentially be infinitely many, but I should at least always find those first two values. And then that's going to get me those inner loop values, right? And then when I go to find the outer loop, I know that I am going to take where did the inner loop leave off. That's where the outer loop is going to begin. And then when I go to find my exit point of the outer loop, I look at, I'm going past 2 pi, and then I'm going to add in this section up here, which in this case was that 2 pi over 3. All right. Okay, so that was a lot. Let's go ahead and take a look at question number 2. So let me erase this since I kind of covered that a little bit. Okay, so for number 2, so the first thing I want to do here is just like the previous problem, is I always want to set that radius equal to 0. So let me square that up just a little bit. Okay, so I want to take this equation right here, and I'm going to let r equal 0, right? So we're always going to let that radius equal 0 because we want to know when it is coming in and out of that inner loop. So I have 1 minus 4 sine theta, and then equal to 0. So again, this would be a good time to press pause and see how you do in solving this. So this one will be a decimal approximation. So make sure you have your calculator handy. So I'm going to subtract 1 from both sides. And then divide both sides by -4. Okay, so if I go and try to figure out, where sine is equal to 1/4, like that's definitely not on the unit circle, right? That's not like 1/2 or √3/2. And so I have to do the inverse of that. So I'm going to do sine inverse of 1/4. And I have to do that in my calculator. And so make sure you are in radians when you type that in. And so when I type that into my calculator, I truncate. So I got 0.252. And then I know sine is positive where y is positive, so up above. So that means this distance right here is that 0.252. And so then I need to figure out, well, what is the rotated distance here? So this section right here is also 0.252, right? So that as well is 0.252. So then to find my quadrant 2, I didn't make it all the way to pi. I stopped right before I got there by 0.252. So I'm going to do pi minus 0.252. And so then my two values for theta are going to be 2.888. And again, you might be off by 1,000th. So like if you're choosing to round instead of truncate, which is fine, right? You can do either one. You just need to be accurate to the nearest 1,000th. Then now I have those two values. Okay? All right, so for this one here, so I have theta is equal to 0.252. So that is going to be this value right here, so 0.252. And then over to here, and that will give me a value of 2.888, right? Okay, so my inner loop, so let me switch colors because it's a little smushed here. So for part A, is going to be 0.252 and then 2.888. Okay, so then here again, so one of the things you might be wondering is up in quadrant 1 and 2, this is where sine is positive, but yet my graph is down below here, which is a very good point, except take a look at this little guy right here. So you see how it says -4 sine theta? So that means that, yes, this is where the sine is positive, but we throw that negative in front of it, and that will drop it down. And so that's why that inner loop is down below. All right, so let's talk about how would I do that outer loop. So remember, we are entering the inner loop, right, the radius equaling 0, at 0.252. And then we are rotating around until we get to 2.888, and that's where it hits the radius equaling 0 again. So it's exiting that inner loop, so to speak, right? So we're exiting here. And so where does it go when it exits that value? Well, then that's when it starts to draw in the outer loop. So we take that number here, and that's the beginning of my outer loop. So my outer loop is beginning at 2.888, so where the inner loop left off. And so then now it's going to continue, right? So it's going to continue around, go to 3 pi over 2, and it's going to keep going until it gets to right there, which is 2 pi, right? So right there is 2 pi, but that didn't quite finish the outer loop, did it? So it needs to go just a skosh more, and that skosh more, that tiny little bit to finish is this distance here, which is 0.252. So then I finished out at 2 pi, and then I went that teeny weeny bit more, which was that number there, so 0.252. And so then I just want to add those two numbers together, right? So don't leave it like 2 pi plus. Go ahead and actually find that value. And so that would be 6.535, okay? And that would be my outer loop. All right, so I know that can be a little bit tricky, so you can either rewatch the video or maybe watch one of the homework help videos and kind of see how you're doing. But definitely make sure that you try the problem first and then watch the video second, just to kind of give you time to process and think about how to do those problems, because they can be a little bit tricky. All right, so the next ones that we're going to be looking at are the pedal graphs. So I'm getting a little sideways here. All right, so for the pedals, so this is not going to be any different really than the previous two, just maybe a little bit easier, which, like, you know, who doesn't love that? Okay, so for this section here, so we are asked to find our alpha and beta values still for the restricted piece. So we are in particular looking for what would graph one pedal. So we have 5 pedals to choose from. So I'm going to tell you which pedal. You don't get to go eeny, meeny, miny, mo. And I want you to choose the pedal that is centered on theta equals 0. So if I take a look here, so this is where theta is equal to 0. So the pedal then that we're trying to find is this one right here, right? So this is the pedal that we're trying to find. And so that's why we have our alpha and beta values there. Okay, so alpha and beta. All right, so one of the things that sometimes throws students off is like it says, well, theta on, theta is equal to 0. So that doesn't mean let theta equal 0. That's just identifying which pedal to be working with, right? So that's not going to play a part into solving. It just plays a part in identifying which pedal I'm referring to. So if we look here, so we're going to have this same equation again, and we want to know when is it equal to the pole. And so it starts at the pole, ends at the pole, and that means that's when the radius is equal to 0. So nothing new from the previous problem, so we're going to go ahead and take that same equation we had, and we're going to equal it to 0. So again, this is a good time for you to press pause, go ahead and try this problem on your own before I do that, right, the solving component. So I'm going to go ahead and divide both sides by 3. And then I want to know, where does cosine equal 0? So cosine is equal to 0 on a quadrantal, and that was at pi over 2 and 3 pi over 2. And then I want to solve for theta, so I'm still working on that. So I'm going to multiply both sides by 1/5. And so then that will end up with theta is equal to pi over 10 and 3 pi over 10. So if we, and then of course there's like a 5 more pair, right? So that 5 theta. So we're just going to always find those first two values though. All right, so if I go ahead and take a look, something doesn't quite add up, right? So, right, because I have 2 values in quadrant 1. So if I look here, 2 values in quadrant 1, so that means, like, if I go up to that first value, right, because that first value I found was pi over 10. So if I try to keep going, I'm going beyond that section that I'm looking for, right? So 3 pi over 10, wherever that is, right? That's like too much, right? That doesn't give me anything about that first quadrant or that first pedal that I'm trying to identify, because I only need one of them in quadrant 1. And so then I know that beta is actually the pi over 10 value, so it's the alpha I'm trying to figure out. So alpha, well, there's 2 ways to think about that. So one is, let me erase this little section here so I can use this up. So one thing that we can take a look at is, I know that theta equaling 0, right, it also has a value of 2 pi. So that would be 20 pi over 10, right? So if I look at that and I use symmetry, so if it's pi over 10 above, it would have to be pi over 10 below as well, right? So that would put me at 19 pi over 10. And so that is a common thing that students will think, oh yeah, 19 pi over 10. Except for that won't do it for us, right? Because that means I'm starting at pi over 10 and I'm going all the way around until I get to 19 pi over 10. Well, the problem with that is that's the other 4 pedals, which is not what I want. So the 19 pi over 10 is not going to work for us. So we have to figure out a different game plan, right? Because that will give me 4 petals on the other side, which is not what I'm looking to do. So what we have to think about is still go back to that same idea that this is theta is equal to 0, right? Which was kind of that describer. So instead of saying, well, that's 19 pi over 10, just think of it as going backward. So negative pi over 10, right? So if we go downwards clockwise, that is a negative direction. So then what if I go between negative pi over 10 and pi over 10? So if I do that, that will give me that petal that I'm looking for. So pi over 10 is my ending, and then negative pi over 10 is my beginning. And so then my domain restriction would be negative pi over 10 to pi over 10. So another thing to kind of think about as far as that goes is we know that we have to cross that theta equals 0, right, because that given piece. And so the only way that's going to occur is if I go from a negative to a positive value. So if I look here, I'm going from a negative to a positive value, and the only way that can occur is if I cross theta equaling 0. And that is actually kind of a theorem that we use in calculus occasionally, which is called the intermediate value theorem. So just kind of a sneak peek. All right. Okay, so go ahead and press pause and try number 4 yourself. And then if you're not sure how to ever get started, you can always, here's the first step and then press pause and try that. And then here's the second step, then press pause and try that. But you should always try to do the problem yourself a little bit before you just sit and watch it. Okay. So here we go. So in this particular problem, we are searching for the petal that is in quadrant 1. So I actually have 2 of them in quadrant 1, don't I? So I have this one here and this one here. So if I take a look at the other piece of the directions, it says the petal closest to the polar axis. And so this is our polar axis here. And so the one that is closest then is that bottom one. So then the one I'm searching for is, let me get out of that, is this one right here. So I want to try to find this guy right here. Okay. So that petal is always going to take on that shape when it enters and exits the pole, and that is going to always occur at r is equal to 0. So I'm going to take this equation right here, and then I'm going to let r equal 0. So I have 4 sine 4 theta, and then equal to 0. And then, again, you should press pause, try to solve that yourself first. So I'm going to divide both sides by 4. And then I know that sine is 0 on the quadrantals, 0, and also on pi, right? So you always want to try to find those first 2 values. And then I'm going to solve for theta by multiplying both sides by 1/4. And so when I do that, I would get theta is equal to 0 and pi over 4. Okay. All right, so for this particular problem, so let me go ahead and mark those out. So I know that theta is equal to 0 right here. And then pi over 4 is over here in the middle. And so if I look between 0 and pi over 4, that gives me the petal that I'm looking for. So there are my alpha and beta values. So then the answer or the domain restriction would be from 0 to pi over 4. Okay, and that's it. That's the last lesson in Unit 10.